Structures of ionic solids. So we looked at different ways that spheres can pack together. When we look at ionic compounds, their structures, their crystalline structures are going to be similar to those unit cells, but we have sort of a complicating factor here that we have two different kinds of particles going together. We have cations and anions, right? And sometimes we have equal numbers of cations and anions, and other times we have like 2 or 3 anions to 1 cation, or vice versa. So when we're talking about ionic compounds where we have cations and anions, then when we're looking at the coordination number is going to represent the close cation-anion interactions. When we just looked at the unit cells for atoms, it was individual atoms touching each other. Here, when the ions are close together, we want them to be oppositely charged ions. Otherwise, they're going to repel each other. But those cation-anion interactions lower the potential energy, and the lattice will only form if the energy is lowered. So generally, the more similar the size of the cation and anion, the higher the coordination number. So if the cation and the anion are the same size, they can pack together in a better way, and you're going to get a lower energy. So when we look at these crystal structures, we're balancing coordination number, charge neutrality, because the charges have to add up to be neutral, and different ion sizes. So if your ions are similar in size, so an example of this is cesium chloride. We have the chloride ions occupying the lattice sites of a simple cubic cell. So if we ignore the purple, the green ones are doing that simple cubic cell, where they're just stacked in nice rows and in all directions. This purple one is fitting into a hole between the rest of these. This is not a body-centered cubic. This is a simple cubic. The cation fits into the holes. So we have a coordination number of 8, and the unit cell contains one of each ion, 1 cation and the equivalent of 1 anion, because we've got 8 anions at the corners here, and we've got 1/8 of each of them. That make sense? Other ionic compounds where we have a 1-to-1 ratio and similar size also form this structure. Calcium sulfide is another example. What if the cation and anion are not different, are not the same size? They are different. So sodium chloride. Sodium ions are much smaller than chloride ions. And if we didn't have to worry about charges, we could actually fit a whole bunch of sodium ions around the chloride ions. They could pack in there much more efficiently, but it has to be charge neutral. So we have to have equal numbers of sodium and chloride ions. So that limits our coordination number to 6. So the way these arrange is the chloride ions occupy a face-centered cubic structure, and the sodium ions are in between them. Kind of looks like a funny jungle gym, doesn't it? So this is called a rock salt structure, and each of these unit cells contains 4 of each ion. So the chloride ions, and we generally focus on the anions because they tend to be the larger. So the chloride ions are in a face-centered cubic, and if you forget how many atoms are in a face-centered cubic unit cell, either imagine or draw it out, and you should be able to figure it out, even if you didn't memorize it. But there's four atoms in a face-centered cubic unit cell. So there's 4 of the chloride ions, and the sodium ions are in between them, and so we're going to have 4 of the sodium ions as well. So that was a moderate size difference. When the size difference is large, then the coordination number is going to drop to 4 because of the sizes, the way they're arranged changes. This is known as the zinc blend structure. So here we have for zinc sulfide, we have the sulfide ions again occupying face-centered cubic, but now instead of these zinc ions being in between them, they're occupying half of the tetrahedral holes. Like, okay, I just got a handle on what a tetrahedra is. What is a tetrahedral hole? So if you have 4 ions here, they can make a tetrahedron, and in the center of those is a space, and that's called the tetrahedral hole. So here we've got this one, and this one. These are 4 arranged in a tetrahedron, and the zinc ion is sitting in the hole. There are actually 8 tetrahedral holes in this unit cell, but the zinc ions will only be in half of them because we have to have a 1-to-1 ratio. Any questions? If you have unequal numbers of ions, like a 1-to-2 ratio of cations to anions, then you can have something like this. This is called a fluorite structure. It's named after a mineral that does this structure, calcium fluoride. So in calcium fluoride, we have 2 fluoride ions for every calcium ion. So the calcium ions are occupying a face-centered cubic structure, and the fluoride ions, instead of being in 4 of the tetrahedral holes, they're in all 8 of the tetrahedral holes, because we need a 1-to-2 ratio. We need twice as many fluorides. So this unit cell is going to have 4 cations and 8 anions in it. If we have a reverse of that, maybe we had something like sodium oxide, Na2O, where you have 2 cations for every anion. You're going to have the same structure, but the anions are going to occupy the face-centered cubic, and the cations will be in the holes. And because it's opposite, that's called an anti-fluorite structure. I think one of the most confusing things about this sort of information is, how much of that do I need to remember? This is a question that should help us understand kind of how do we even think about this. This is really more of an introduction to these ideas rather than, we're not going into details and requiring mastery of this topic, but you need to have heard about these things. So a question like this: which compound is most likely to crystallize in the zinc blende structure? Okay, we're not talking about that many structures here. This is the fluorite and anti-fluorite structure. Fluorite is a 1-to-2 cation to anion ratio. Anti-fluorite is the opposite, 2 cations to 1 anion. So that's when you have a 1-to-2 or a 2-to-1 ratio. If we have large size differences but a 1-to-1 ratio, that's where we have that zinc blende structure. A moderate size difference, we're going to get this simple cubic cell. I'm sorry, that's not the simple cubic. I thought it was on a different slide. Sorry, rock salt. Ions of different sizes, but the difference isn't that big. Rock salt structure. And this is ions of similar size, the simple cubic. So if we're doing zinc blend, what are we looking for? What would the ratio of cation to anion be in the zinc blend? So fluorite was the 1-to-2. Anti-fluorite is the opposite, 2-to-1. So this is zinc blend. What's the ratio of cation to anion? It's not 1-to-2. What's the other one? It's not 2-to-1 either. It's 1-to-1. This is just equal numbers. Size difference. Is this a big size difference, a medium size difference, or the same size? Let's go back and look. Okay, so this one was unequal numbers. This is large size difference, zinc blend. So we're looking for large size difference. Rock salt is moderate size difference. So for zinc blend, we're looking for large size difference. Okay, let's look at the ratio first. Is this one a 1-to-1 ratio of cation to anion? Yes. Is this one? No. So this second choice, B, is a 1-to-2. That's probably going to be a fluorite. It can't be zinc blend because it's got the wrong ratio. So that one's out. Is this one 1-to-1? Yeah. So A and C are the possible choices. And then we're going to look at what's the size difference between the cation and the anion. So here we have 148 versus 181. Here we have 96 versus 216. You want to choose the one with the larger size difference. So that would be C, right? This would likely have the rock salt structure where it's a smaller size difference because there is a size difference here, but it's smaller than that one. This, based on the limited information I've given you, this I would expect you to predict might have a fluorite structure. So keep in mind there's a lot of other structures. We're just telling you about some of the more common ones. Any questions?